you. Thanks, everybody. It's a little odd seeing you guys with this particular seating setup. It feels a little like talking in front of a school cafeteria. But we don't have much time, so I'm going to get right into this. We'll talk a little bit about the history of DNS security, such as it was, and then from there we'll look at the advent of kind of the first protective DNS solution, which is something called response policy zones. And then we'll talk a little bit after that about passive DNS. If we have time, we'll talk about the Infoblox approach to creating threat intelligence. If not, that's okay. I know that my colleague Casper talked about it some in a previous presentation. So, history of DNS security. Way back when, roughly actually when I started in the world of DNS, 1983, 84, the beginning of DNS, there were two security features in DNS servers. One was that DNS servers would not accept responses from IP addresses that they had not sent queries to. That's barely a security feature, right? That's just common sense. If you didn't ask a question and you get a response, you should probably throw it on the floor. The second security feature was that when a DNS server would send a query to another DNS server, it would stamp that query with a random message ID. The message ID was between 0 and 65,535. So it's a 16-bit value. When the DNS server received what was ostensibly a response to that query, it would check that it actually answered the question that it had posed, but it also checked that the message ID matched the one that it had specified, right? The idea being that somebody who was not a man in the middle couldn't just spoof a response, that this was actually a response from the DNS server that we had queried. That was it. Two security mechanisms for many, many years. Right. Unfortunately, since pretty much the beginning of DNS servers have been the targets of attacks and they have been accomplices in attacks on the internet. Back in 1997, some of you may be old enough to remember this, there was a guy named Eugene Kasparev. Kasparev mounted the first cache poisoning attack on the internet. He redirected folks who thought they were going to the Internics website to his own website using cache poisoning. The Internic back then was the one place you could go in order to register subdomains of com, net, and org, the three big generic top-level domains. Kasparev believed that that was an unfair monopoly, and in fact it was, and we later got around to breaking up that monopoly and instituting the system of single registry, many, many registrars that you have today. But Kasparev kind of took matters into his own hands, mounted this cache poisoning attack, redirected people who thought they were going to the Internics website to his website where he had this screed across the middle of the website decrying the unfair monopoly and so forth. Right. So we should give him a certain amount of credit. He didn't really do this for direct monetary gain, right? He didn't impersonate the Internics website. It was obvious that you were in the wrong place when you got there. That did not help him so much when he was apprehended by the Royal Canadian Mounted Police and extradited to the US to face charges. But this was an implementation flaw in the most common DNS servers at the time. We pretty quickly figured out what the implementation flaw was. We patched it and we went on. In 2001, we had another big vulnerability in bind 8.2. Unfortunately, we introduced a buffer overrun in the code. And a worm called the lion worm used that buffer overrun to transmit itself from system to system across the internet. And wouldn't you know it, the code that we were adding that introduced the buffer overrun was transaction signatures. So we were trying to introduce cryptographic transaction signatures to DNS to improve the security of DNS, and instead we introduced a buffer overrun. Again, just an implementation problem. We fixed it, we went on. In 2007, a guy named Amit Klein, who was then the chief technology officer of a company called Trusteer, did an analysis of the pseudo-random number generators that we were using in DNS servers at the time. So the pseudo-random number generators, or PRNGs for short, they were the routines that were responsible for coming up with those random message IDs, right? That's really important that they be random because you don't want someone to be able to guess the message ID that you've come up with, right? You want the DNS server on the other end to have to see that message ID. And he did an extensive analysis of the PRNGs that we were using to determine how random they were. And I don't want to get too technical on you, but the one in Bind was crap. It was terrible. And if you saw 14 consecutive message IDs that it generated, you could reproduce the internal state of the PRNG, and you would know from that point forward every message ID that it would generate in the order in which it would generate it. Again, implementation problem. There are better PRNGs available. We grafted one into Bind, and we went on. In 2008, less than a year later, a guy you probably have heard of named Dan Kaminsky found a systemic vulnerability in DNS to cache poisoning. And by systemic, I mean this is not particular to any implementation. This is not an implementation flaw. This is something that is common to every DNS server that implements the DNS specifications. And we were incredibly fortunate that Dan was a white hat hacker. He let all of us within the sort of small DNS community know about the vulnerability before it became public, and we had a head start in figuring out how to address it. Unfortunately, it became public before we'd intended, but at that point we'd already sort of implemented workarounds. In 2016, right, recent enough for many of us to remember, the Mirai botnet was used to mount an enormous distributed denial of service attack against a company called Dyn, D-Y-N. Dyn ran external DNS zones for many of big companies on Wall Street. For example, they ran the PlayStation Network, they ran Twitter's DNS presence, they ran the New York Times DNS presence. And so for the amount of time that they were unavailable, that their DNS servers were not responsive, it looked like the internet was down. And then on an ongoing basis, we find that DNS servers are used in DDoS attacks themselves because DNS servers make really good amplifiers. You can send a relatively small query to a DNS server and get a large response back. You can get about 100-to-1 amplification. And most DNS traffic is UDP-based, so it makes it very easy to spoof the source IP address and get that amplified traffic directed to a target of your choosing. Now, we weren't sitting still while all this was happening, right? For the first 2 decades of DNS's existence, we were hard at work implementing DNS security mechanisms. But these were, I would say, fairly rudimentary mechanisms. So we had to do IP address-based access control lists on zone transfers and queries and dynamic updates. We did TSIG, which, as I told you, we got wrong initially, which created a security problem within Bind, but then we fixed that implementation. And we spent a lot of time on something called the DNS security extensions, which are cryptographic security extensions that allow you to digitally sign DNS zone data, and that allow suitably configured recursive DNS servers to cryptographically validate that data and determine that it really came from the people who signed it and that it hasn't been modified since it was signed. So all of that's important, but unfortunately, people were still using and abusing DNS in all kinds of ways. Here's a rundown of the ways in which DNS is involved in, say, a phishing campaign, right? The bad guys go out, they register some brand new domain name. Maybe this domain name incorporates, say, some trade name or brand name that you're familiar with or something that actually looks like it. They registered the brand new domain name because it has no reputation associated with it, right? It hasn't been implicated in malicious activity yet, so nobody's blocking it. Then they lure unsuspecting users using some phishing campaign to websites with this particular domain name. And their devices become infected when they visit that website. The malware wakes up on these devices. One of the first things that it wants to do is rendezvous with some command and control infrastructure out on the internet, something that will tell it what to do. Should I scan the local network? Should I, scan the local file system for files that might contain passwords or credit card numbers or what have you? Should I just start exfiltrating data? Right? Now, the way that that happens is almost universally with DNS. In the early days, malware would just look up a particular domain name that represented its command and control infrastructure, but we pretty quickly got wise to that and started blocking that. So then the malware would hunt through a giant list of domain names until it found an active command and control server. Well, you can block that too. So then the bad guys came up with the idea of a domain generation algorithm. And this is code that synthesizes different domain names on a temporal basis. So maybe every 5 minutes or every hour it generates a new domain name, probably from a hash function and then some list of concatenated suffixes. And it comes up with these domain names every hour, looking them up until it finds one that maps to an address, and that address actually has active command and control infrastructure running there, right? But that's the way that it rendezvous with the command and control infrastructure. Very, very difficult to block that because over time, the domain generation algorithm may generate tens of thousands, hundreds of thousands, or even more domain names. Right? And we can't block all of those. Once the malware actually finds something on the file system of the device it's running on and wants to exfiltrate that, one of the techniques that it may use is DNS, because you can tunnel data through DNS, right? You can embed data that you want to exfiltrate to the internet in queries, right? And then in the responses that you get back, you get acknowledgments, or you get, for example, commands from a command and control server. All of that is possible. It's not fast, but it doesn't have to be, because in the vast majority of cases, no one's looking at it. Nobody's examining that traffic. And unfortunately, through all of this, DNS has been blindly complicit. DNS simply doesn't know anything about it. Right? Up until 15 years ago, you could send virtually any DNS server on the internet a query for anything, the address of www.malware.org, and it would go, here you go. So, a very smart guy who I've known for many decades, a guy named Paul Vixie, back in 2010 said, look, enough of this. We have too many people abusing DNS in order to do this. And we have organizations around the internet that actually run, for example, captured specimens of malware and determine what domain names that malware looks up, what domain names it relies on, right? Or they disassemble it. Or we have organizations like Spamhaus and Serble that run hundreds of thousands of spam traps and who capture the spam and analyze it to see what links represent malicious websites or other malicious resources, right? Thereby compiling lists of all these domain names that we know are malicious. And if we could just get these databases of known malicious domain names close to our DNS servers, we could tell the DNS servers, if you get a query for one of these domain names, don't answer it. Lie. Say that domain name doesn't exist. And by doing that, you can save yourself a tremendous number of headaches, because even if the malware gets into your network, right, even if somebody pulls off one of these phishing campaigns, somebody tries to click on the link, it doesn't go anywhere. The malware gets onto your network, tries to reach back to command and control infrastructure, and it can't get there, right? So Paul and I have known each other for a long time. I asked him for a favor. I said, do you have, any particular memories of when you posted your blog called Taking Back the DNS that described the situation? And he said, yeah, I do have a photo, and he sent it to me. Here it is. This image plays a lot better in Protestant countries. I don't know why that is. Unfortunately, you show this in the US, and people go, who is that? All right, so the idea that Paul and his colleague, Vernon Shriver, came up with is something called a response policy zone. And a response policy zone is actually a pretty simple idea. It's really just a repurposing of the zone in DNS to encode policy. And the policies allow you to say things like, if somebody looks up this domain name, don't go out and resolve it, send back this error, say that domain name doesn't exist, or say there is no data of that type associated with that domain name. So that if somebody looks up www.malware.org, you can just say, sorry, NX domain, that doesn't exist. Simple idea, right? Very quickly after this idea came out, people realized that we had a built-in publication and subscription mechanism with these response policy zones, because we've been moving zones around the internet for decades, right? That's what primary and secondary DNS servers do. And we've been tuning those mechanisms over time, right? So that primary DNS servers can tell secondary DNS servers when a zone changes. That's what a notify message does. The secondaries can turn around and request incremental zone transfers, just the changes, in case the zones get very large. So a lot of organizations like Spamhaus and Serble that had traditionally been in this block list business said, oh my gosh, this is a much more convenient way to publish this data. right? And rather than making some file full of JSON available to somebody to download and reformat, they can say, oh, we stood up a primary DNS server, just configure your secondaries as secondaries for this zone. You can pick up all of our reputational data and apply it in one fell swoop. It's a very exciting diagram here showing how this works. Here's the recursive DNS server in the center. Here's the primary over here. We get the information via zone transfer. And then here's some client. When the client sends us a query for some domain name, we check the response policy zones that we have loaded to see if we have any relevant policies. If we do, we log the fact that, that this client sent that lookup, and we send that error or redirection based on the policy. Very simple. So this became really the first technology in a whole group of technologies that we've come to call protective DNS, right? This is DNS infrastructure with the intelligence to determine whether a query is for a malicious domain name, a suspicious domain name, or a completely benign domain name, and to take action appropriately. Now, as we said when we went through that sort of life cycle of a malware campaign or a phishing campaign, the great thing is DNS is used over and over and over again. The bad guys rely on it just as much as we do, right? It's used in the initial phishing campaign. It's used to rendezvous with command and control infrastructure. And we know in many cases which domain names are going to be looked up. And if we can interfere with that, if we can subvert it, we can prevent these malware campaigns from actually working. DNS infrastructure is already pervasive. All of you on all of your networks have DNS servers. So we're not talking about something new that you need to put on your network, right? It works with basically every type of device that you might have out there. We're not talking about some specialized piece of software that you need to install everywhere. Everything on a TCP/IP network sends DNS queries. So we can protect all of those devices, whether they're IoT devices, whether they're mobile devices, doesn't matter. We can protect it via DNS. It works with basically every protocol, not just those that are proxyable. And it's fast. It adds almost no latency to transactions, right? It's scalable. It can handle literally millions, in fact, tens of millions of indicators of compromise. And that's important because that's how many we have. We have literally tens of millions of indicators of compromise in our feeds today. That's how much DNS we know is bad and malicious and will hurt you. It's also very effective. Ann Neuberger, who was the director of the NSA's cybersecurity directive, this was several years ago, but her estimate was that about 92% of malware would be completely neutered or thwarted by deploying protective DNS. So there are some limitations of response policy zones in protective DNS, unfortunately. They're inherently reputational. They're basically big lists of domain names and IP addresses that we know are malicious. And there are some times that we don't necessarily know what the domain name is, right? DNS tunneling, for example, when someone's embedding data in some dynamic way into upstream queries and responses, or domain generation algorithms. And in those cases, we turn to something called passive DNS. This is a photo of the inventor of passive DNS, Florian Weimer, fellow European. I should ask Florian for a better photo. This is him asking a question at a conference, I think. But basically, passive DNS is just telemetry, DNS telemetry, a record of all of the responses that a DNS server has received, whether those are answers or referrals or errors that are consolidated and then replicated somewhere. And so I have a very exciting animated sequence here where you have a recursive name server in the center. It gets passive DNS data from, the answers that it gets from root servers, COM servers, anything else that it talks to, and then it replicates that to a passive DNS database. In case you missed that, we'll go back there. There it is, well, all right. So the passive DNS database, that could be your SIM, it could be a dedicated passive DNS database, it doesn't matter, just that you're collecting all of that data. And what do you do with that data after the fact? Well, you can mine that data. That's your data. It's produced by devices on your network. And you can find things like fast flexing, you can find domain generation algorithms, right? You can find DNS tunneling. The way that you find these things is by algorithms, right? some of them fairly sophisticated machine learning algorithms, but the great thing is that those algorithms, a lot of them were developed in academia. I have a couple of friends, Manos Antonikakis and David Dagon. They run a lab at Georgia Tech in Atlanta. This is what they specialize in. But Georgia Tech is a publicly funded university. They publish all of this in papers. You can just download them and implement it, right? And of course, we at Infoblox implement these things too. So that brings me to the last couple of things. But before I talk about this, I want to take just a brief minute to say something. And that is, well, first of all, apologize about Greenland. But second of all, the one thing I wanted to say about this is protective DNS. No matter who you use, which vendor you use to do it, or whether you use open source to do it or whatever, it is an absolutely critical tool in your security tool chest. So I happen to work for Infoblox. I happen to think we do this well, but that doesn't matter. Just do it, right? It's really, really important to have these mechanisms at your disposal, right? So, yeah, sure, look at us, look at our technologies and our feeds, but even if you don't choose us, please look very closely at protective DNS, if you don't have it already, and at implementing this on your network. So, as I said, there are a few different ways that you can build these response policy zones. One is to have all these spam traps, catching spam, analyzing that email for links and determining which are malicious. You can disassemble captured malware. You can run captured malware on isolated networks and see what DNS queries are sent. The problem is that in each of these methods, the attack has to be underway, right? So it's in a way too late. You may have already fallen victim to it, right? Somebody may have already clicked on the link. So there's also a fundamental scale issue here, which is that the bad guys write malware faster than we can disassemble it, faster than we can capture it. We don't have enough computer science grad students to turn into threat researchers in order to keep up. So another way of doing this, which is what Infoblox does, is to start with passive DNS and domain registration data and to write machine learning algorithms to analyze that, and to analyze, in particular, the attributes of this data and detect anomalies and detect patterns. And the great thing about that is that scales, right? If what you find, for example, is that there are 75,000 domain names all registered to the same set of DNS servers that host all kinds of other malicious domain names, well, that makes them inherently suspicious. And we can add those 75,000 immediately to our protective DNS files, right, to our response policy zones. So I don't really have time to go through this example, but one of the things I wanted to talk about is, hey, we can understand the way to do a lot of this, right? Bad guys, for example, register a whole lot of lookalike domain names, and they lure unsuspecting users to those. They may try to get you to click on a link because they're claiming that you forgot to pay a toll on a toll road somewhere. I don't know if that happens here in Denmark as much as it does to me. But we can detect these sorts of things. So for example, if we're monitoring strings like, say, Amazon and Google and Infoblox, just as an example, right? We can look at passive DNS data and domain registration data and look for domain names that contain those strings, or that contain those strings with common substitutions, what we call lookalike glyphs, like a lowercase l and an uppercase I or a 1, those sorts of things. And then when we find them, we can look to see whether they're actually the same. Are they owned by the same organization? So if we find buy-amazon.com, for example, we can say, what are the DNS servers for buy-amazon.com? What are their IP addresses? Are they in autonomous systems that are actually owned by Amazon? Are they the same set of DNS servers as those for Amazon.com? If they're not, right, if they're in Tajikistan, that is suspicious. That we would probably want to flag. And this is actually a service that we offer, lookalike monitoring for people who have brand names and trade names that they want to be able to defend. And we also have a takedown service. So if we find these things, we can have them taken down for you, right? Unfortunately, it gets even more complicated because of something called IDNA, Internationalized Domain Names and Applications, which allows you to put Unicode characters and domain names. You can see this is actually a section of Unicode for Cyrillic. You can see how many, what we call homoglyphs there are here. That certainly looks like a lowercase a, but it's not. You put that in a domain name, say in paypal.com, but with 2 of those, it's visually indistinguishable from the real paypal.com, but it could go to a completely different place. I'll skip this. So we offer lots of services, lots of feeds with all of this information. I think we do a very good job of it. Typically, with our suspicious domain feeds, we can provide 63 days of advanced warning. We will put a domain name into our feed 63 days before it's actually used in anger. Our false positive rate is vanishingly small, 0.0002%. 4 million malicious and suspicious domain names added. And as I said about the magnitude of the threat, it is enormous, absolutely enormous. Almost 20 million suspicious domain names, another 25 million, 26 million that are known malicious. This is what you have to block. And there are no technologies out there that can block as quickly and as effectively as DNS. But the one thing, again, I wanted to say about all of this is, even if you don't do any of this with Infoblox, please at least look at protective DNS as a technology. All right, I don't want to run too much over. Thank you all so much for your attention. Appreciate it.
Hi, Cricket. Thank you for doing this presentation, and hopefully all our guests is a bit curious about how to do DNS security going forward.
Helps.
And unfortunately, I don't have as good stories as Thomas around why you should have a gift, but I actually figured out that this little ape done by a Danish guy called Kai Bøjesen, initially it's invented for 3 things, and that's where the analogy comes in, because besides DNS security, you do DNS, DHCP, and IP address management. This was initially designed to wear a hat, a coat, and a scarf. But thank you for being here.
Thank you, Jimmy.